Hi, I am Cemre and I'm a postdoctoral researcher at the University of Surrey. As a part of the University and Defense research collaboration, we targeted the automatic detection of anomalous ferry tracks in the English Channel. Basically, our aim was to address the problems of navigation surveillance and detection of illegal traffic activities such as piracy, drug smuggling, and terrorism. And of course, to reduce the workload of operators by providing them with automatic anomaly detection algorithms. So, we have carried out this work on the data collected by our collaborator, Thales UK, at the Solent area in July and August 2012. The data was based on AIS signals, which provide second-by-second information about the latitude and longitude for each ship. In this example map, you see tracks traced by multiple ships, including ferries between Portsmouth and the Isle of Wight, where each ship trajectory is represented by a different color. For our framework, we have employed a bottom-up approach, which means that instead of a rule-based system based on instructions defined by the subject matter experts, we have modeled the so-called normality from the given data automatically. Anomaly detection was then carried out using a suitable metric. I have to underline that the data was unlabeled, which means that it included anomalies as well as normality. So, to tackle this, as a first step in the algorithm, we used a data cleaning system where the unlabeled anomalous or so-called corrupted training data were purified from the outliers automatically. This was applied prior to training by using median absolute deviation cleaning on features we extracted in order to avoid making unrealistic assumptions about the AIS records. In our approach, three critical features for the maritime analysis of a ferry ship were taken into account. First of these features was direction, or in other words, heading. During training, while modeling normality for direction, we have followed a hierarchical Markovian approach based on grids. As for the second set of features, displacement and location was taken into account, and Gaussian process regression was used for the modeling of these. Both the Markovian and the Gaussian process-based models were generated for each input ship. Let us start by showing an example normal path taken by the hovercraft when it departed from Isle of Wight and traveled up to Portsmouth. In the background in white, you see all the training trajectory samples traced by this ferry previously. These are raw samples before the application of any processing like cleaning. In the foreground, we see the coordinates that the ship is sailing on second by second. The color blue indicates if a point is classified as normal, and as we can see, all the points in this trajectory are colored in blue. For a second example, we are looking at the training and test data of the same ship, this time while taking off from the opposite port, Portsmouth, and arriving at Isle of Wight. Although everything was going on smoothly, a sudden direction change flags the anomaly detector responsible for direction, and this gets colored green. In the final example, we demonstrate a case full of anomalous points. As we see here, the ship starts moving normally, but then changes direction in an unexpected way, which is indicated by the color green. It later on continues showing unexpected behavior and becomes an anomaly in terms of its location in the area of interest. And the location anomaly is indicated by yellow color here. Finally, it comes back to the port by taking another unexpected direction during approach. I would like to note that this last trajectory was later on analyzed by an expert, where he guessed the ship of interest as being actually a yacht or a leisure boat whose ID was probably mistaken for a ferry. To be able to calculate the accuracy and evaluate the performance of the algorithm, the anomalous trajectories for a ferry were hand-labeled. It was shown that using 90% confidence interval, we were able to obtain a 93% detection rate for anomalies and a 2% false positive rate. If we wanted to detect all anomalies, then our false positive rate became 6%. For clarity, a demonstration of routes which were detected to include anomalies more than 1/3 of their length is given in this picture. The color yellow depicts the routes labeled as normal and red as anomalous. Although the main users for this technology would be Royal Navy, other forces such as Royal Air Force would also benefit from it, for example, for aerial anomaly detection. As the nature of the approach permits, it is transferable to likewise domains.